Hello student, welcome back to the one more session of Analog and Digital Electronics. This is Vasan Naik from Canara Engineering College. In this session, we will study up-down counter. In my previous session, we have covered what is counter, what are the different types of counter. Other than that, what is the up counter, what is the down counter, etc. Let me review few of the points before proceeding to up-down counter. What is the counter? Counter is a electronic device which counts clock cycle. There are two types of counters we know. One is called as a synchronous counter, other one is called as asynchronous counter. The difference between synchronous and asynchronous is synchronous is faster than asynchronous. So the other difference is, like in asynchronous, we feed the clock to the first flip-flop. The output of the first is connected as a clock to the second, and output of the second is connected as a clock to the third, so on. In synchronous, all the flip-flops are driven by same clock signal. Depending on the number of states the counter goes through, the mod of the counter will be decided. For example, mod 8 counter is nothing but the counter which counts from 0 to 7 state. Mod 5 counter is the counter which counts from 0 to 4 states. So up counter is the counter which counts in upward direction, and down counter is the counter which counts in downward direction. In this session we will see binary up-down counter. So binary up-down counter is the counter which counts in both up direction and as well as down direction. So in order to design binary up-down counter, we need two control signal. That is, one control signal is U, which counts in upward direction. When this control signal is enabled, which the counter will count in the upward direction. Other control signal is D. When this control signal is enabled, the counter counts in the downward direction. Here, the diagram shows the state graph and table for up-down counter here. The initially counter will be in the state 0, 0. When it works in the upward direction, then the next state will be 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. From 1, 1, 1, it moves to 0, 0, 0. Suppose the counter counts in the downward direction, then from 0, 0, 0, it moves to 1, 1, 1. From 1, 1, 1, it moves to 1, 1, 0. 1, 1, 0, it moves to 1, 0, 1. 1, 0, 1, it moves to 1, 0, 0. 1, 0, 0 to 0, 1, 1. 0, 1 to 0, 1, 0. 0, 1, 0 to 0, 0, 1. 0, 0, 1 to 0, 0, 0. Here you can see the present state of the counter and the next state of the counter. The present, since it is a 3-bit, since we are going to design 3-bit counter, or mod 8 counter, here the present state is represented in 3-bit form. So we are taking 3 input to the counter, 3 output of the counter, A, B, C. So there will be 8 combinations. Similarly, next state is represented here, but next state depends on the control signal. When U is equal to 1, it works like a upward counter. When U is equal to 0 and D is equal to 1, it works like a downward counter. So in the next slide, we will see how to design mod 8 counter by using this truth table. So after writing the transition table, and by using present state and next state, you have to solve this one by using K-map. When you solve this one by using K-map, in the next slide you will see here, you will get the expression that is DA, DB and DC. DA is nothing but A exclusive OR with U plus T. DB is nothing but B exclusive OR with the UA plus DA bar. DC is nothing but exclusive OR with the C plus UBA plus DBA. So students, you have to make a note here. See, we have two control signals here. That is U and D. Suppose U is equal to 1. So U is equal to 1, the counter works in the upward direction and it is called as up counter, and D is equal to 0. So we'll substitute this value in this equation. When U is equal to 1, So 1 plus 0, so that is nothing but A exclusive or with 1, and you will get here A bar. Similarly DB, you will get this value. Similarly DC, you will get this value. And when U is equal to 0 and D is equal to 1, you will get this value. For DA this value, DB this value, and DC this value. Now you have to represent this one in the design. So for design purpose, I have taken here 3 flip-flops. So the first one is A, second one is B, and third one is C. So all the flip-flops were driven by same clock. Here it is represented separately, but it is connected to single clock. Other than that, we have input D, A, DB, and DC. So now DA is nothing but A bar when it is U is equal to 1 and D is equal to 0, when U is 0 and D is equal to 1. So that is represented here by using exclusive OR gate. So exclusive OR gate, A is connected as an input to the exclusive OR gate, and other input to the exclusive OR gate is nothing but OR combination of D and U. So based on OR combination of D and U, the output of the exclusive OR gate is nothing but A bar. It will be A bar. Now DB is nothing but so here DB is nothing but B exclusive OR with the UA plus DA. So let me take exclusive OR gate. So one input to the gate is nothing but B. The other input to the gate, other input to this exclusive OR gate is nothing but it is the combination of UA, this signal is A, UA, and DA bar. So I am taking UA is given to one AND gate and DA bar is given to other AND gate. Output of UA and DA is summed together using OR gate, and output of the OR gate is given to exclusive OR gate. That is DB. DC is nothing but one input to the exclusive OR gate is C itself. The other input is based on this expression UBA DB bar A. So let me take here one OR gate. So output of the OR gate is connected to exclusive OR gate, and the input to the OR gate is two components. One is UBA. So this is B and this is A. UBA, and the second component is DB bar A bar. So second component is DB bar A bar. Like this, we have connected all the inputs to this flip-flops. Now let's write the output of the counter. So the output of the counter is this is QA or A or QA, this is QB, and this is QC. So let me write here, this is QA and this is QB and this is QC. So this counter, by using D flip-flop, will count from count in both direction from 0 to 7 or 7 to 0, that is from 0 0 0 to 1 1 1, or from 1 1 1 to 0 0 0, that is both in up direction and down direction depending on the control signal. When the control signal U is equal to 1 and D is equal to 0, the counter will count in the upward direction, that is from 0 0 0 to 1 1 1. When the control signal U is 0 and D is equal to 1, the counter will count in the downward direction, that is from 111 to 000. So in this way you can design mod 8 counter or 3-bit synchronous counter by using D flip-flop and transition table. So students, in the previous session I have completed a synchronous counter, the design of a synchronous counter and a design of synchronous counter, and in this session I have completed the design of up-down counter. In the next session you will see counter for other sequence in the sense like in all these counters, whatever counters so far, whatever counter we have designed, counter design you have seen, in this you have designed the counter for complete value. Suppose I want to design the counter for in-between value. For example, I want to design the counter mod 5 counter. So when you use 3-bit, you can design the counter. When you use 3-bit, you will get 8 combination. But I want to stop the counting at 5. So how to proceed in that way? So how to design mod 5 counter, or how to design mod 10 counter, mod 12 counter. All these things we will see in the succeeding class. Thank you.